Okay, thank you for the introduction. So hi everyone, today I'll present RefinedRust, a new tool we've been developing with the goal of getting high assurances for Rust programs that involve unsafe code. So I'm sure most of you have heard about Rust, but for those of you who don't know it yet, Rust basically aims to be an alternative to C or C++ with zero-cost abstractions for memory management so that you don't have to do memory management manually. And it's enjoying growing popularity. For instance, now Rust has just become the second language after C to be used in the Linux kernel. And one of the reasons for that is that it brings modern programming paradigms familiar from high-level languages like functional programming to systems programming. And another big reason is that it aims to provide memory safety. No null dereferences, no use after free, and no data races, which are big problems for code written in C or C++. And with just that, just using Rust already basically rules out a huge class of common security vulnerabilities in system software in a way that is accessible for common programmers. There's one catch here, which is unsafe code, and I'll get to that in a moment. Now, if you want to get even higher assurances than just memory safety, one way to do that is to do formal verification. And today there are a number of great tools and approaches available for doing formal verification in Rust, like Prusty, Rustorn, Crusoe, Eneas, Flux, and Varus, and a great many other tools. And many of them have already been shown to be of high usefulness in practice. However, there's one catch. They usually leave out one of the most important features of Rust, namely that you can leave the safe fragment and go back to unsafe C-style programming. And that is what's called unsafe Rust. Unsafe Rust basically enables C-style raw pointer manipulation free from Rust's restrictions on pointers, but is no longer guaranteed to be memory safe. So it's kind of a double-edged sword. While most of the time, safe Rust is more than sufficient for everything you want to do, unsafe Rust is really crucial to the success of Rust, because a lot of code that you can safely use in Rust without fear of memory unsafety actually internally uses unsafe code for its implementation. For instance, that is the case for Rust's vector library of dynamically allocated arrays. And in this excerpt from VEC here, you can see how unchecked pointer arithmetic is used to add a new element to the vector. But the problem, on the other hand, with unsafe Rust code is that it leaves Rust's nice safe ownership patterns behind and often is not well behaved. So in a verification tool, you need an accurate memory model to capture the intricacies of Rust's pointer semantics, and you need to explicitly reason about ownership, which makes things much more complicated. And this is one of the reasons why few existing Rust verification tools handle unsafe Rust. Now we want to tackle that problem and create a verification tool that supports both safe and unsafe Rust code. And we call this tool RefinedRust. RefinedRust is the first system that verifies functional correctness of both safe and unsafe Rust code, and moreover, it generates foundational proofs in the Cork proof assistant for high assurances. So the way we do this is to start out with ideas from RustBelt, which is a well-known semantic model for Rust. RustBelt already shows us how to handle Rust's reference types, which are tricky to get right, and it allows us to manually reason about unsafe code. But then we need to figure out how to turn that into a practical verification tool. Reusing RustBelt currently is a lot of manual work, and it can't reason about functional correctness. So for that, we take inspiration from work on RefinedC at PLDI24 3 years ago, which is an ownership-based refinement type system for C. RefinedC combines Rust-inspired ownership types with refinement types for functional correctness reasoning. And since unsafe reasoning is common in C, it also naturally handles kind of unsafe style code with its type system. And best of all, RefinedC's type checking is automated to a fairly high degree using its lithium separation logic engine. Now, of course, combining RustBelt and RefinedC isn't as easy as it sounds, because Rust and RefinedC have incompatible styles of ownership types, and RefinedC style refinements turn out to not really work for Rust. I'll explain some of that later in this talk. But now let's see how to use RefinedRust and how a user would interface with RefinedRust. First, the user writes the Rust code they want to verify and adds specifications in the form of pre and post conditions and invariants to it. I'll explain that more in a bit. Then they run the RefinedRust frontend, and the frontend uses the Rust compiler to translate the Rust code first into the Rust intermediate representation MER, and then further into our model in the Cork proof assistant. And in addition, it also generates specifications for RefinedRust's proof checker in the form of lemmas that will be checked by Cork. And then it calls the RefinedRust proof automation to generate a proof that the code satisfies the specification. And either this proof can succeed or it will fail because the specification is wrong or there's a bug in the code, in which case we should fix these, or we may need to provide some manual hints and tactics to help the proof automation in Cog. And all of this latter part happens inside the Cog proof assistant, so we can assign fairly high trust to it. Now, just to see an example of it, as a first super simple example, let's look at this add42 function from the previous slide. It basically takes a 32-bit signed integer as an argument, and then it returns the result of adding 42 to it. So to specify that this function behaves as intended, we first have to specify a mathematical model for the argument. And in this case, we can introduce a mathematical integer I, and then we say that the argument x has the value I. And then the function should return the value I plus 42. Note that we don't have to specify any types here, but only mathematical values. Now, the mathematical integers in the specification are unbounded, so adding 42 always works. But in the Rust representation, x is limited to 32 bits, so overflows can happen. So additionally, we have to require the precondition that I plus 42 actually fits into a 32-bit integer. Okay, this is pretty simple. Let's look at a more involved example involving actual unsafe code. And for that, let's look at a variant of the vec library for dynamically growable arrays that I mentioned earlier. The vector basically has a raw pointer to a buffer, a length field with the number of currently stored elements in the buffer, and a capacity field storing how much memory is currently allocated for the buffer. Now, to understand how we verify that, let's look at how the vector manages its buffer. The memory pointed to by the buff field basically consists of an initialized segment here in blue on the left, and this contains the elements of the vector, and an uninitialized segment on the right in orange with the over-allocated memory. And our first task for verifying vec now in RefinedRust is to make this representation invariant formal. And kind of we would like to hide all this nasty pointer business or this memory management, and we would just like to abstract the whole vector to the mathematical list of elements contained in the initialized part, and let's call that XS. And then we want to forget about the capacity, for instance. And to do this, we put annotations on the Rust code, and let's see how this looks formally. And we define this representation invariant in multiple steps. First, we have to come up with a mathematical representation for the vector and relate it to the physical representation in Rust. Then we define some invariants to represent the initialized and uninitialized parts. And finally, we need some side conditions to keep everything in sync and constrain the size of the allocation. You don't have to look at all of this in detail. You can find this in the paper. But the most interesting part is that we manually specify a type for the buffer using RefinedRust's array T type. And this is a new type that does not directly correspond to a Rust type, but we need it to crucially assert ownership over the buffer and say which elements it contains. And this also nicely corresponds kind of to the intuitive safety invariant that a Rust programmer might imagine for this vector. Okay. With that, we are ready to actually take a look at some of the key functionalities of a vector in Rust. And one of the key functionalities here is getting a mutable reference to one of its elements. And the function you see here basically takes a mutable reference to a vector self and an index, and it should return a mutable reference to the element at that index, assuming that index is in range. And it is marked as unsafe, as you can see here, because it does not perform any bounds checking on the index. So for the function to behave in a memory-safe way, the caller has to ensure that the index is in range. And that is precisely something that we can specify nicely with RefinedRust. For the specification, we annotate the function again, and we first specify the mathematical values for the arguments, saying that the vector has a list XS and the index is a natural number I. And then we want to specify that we return a new mutable reference to the right element of the vector. And this uses the returns clause, which says that the returns reference contains the element of the list XS at index I. And finally, as I said, you should assume that I is in the range of the list. This is something that the caller has to ensure. Now, there's intuitively some part missing here. Namely, we return a mutable reference, and we can use it to modify the element of the vector at index I. So how does using this mutable reference to modify that element change the whole vector? Well, for that, we introduce a new technique called borrow names, which communicate the final value of mutable references. And we say that the mutable reference to self uses the borrow name gamma for its final value, and the returned reference gets a new gamma I that is existentially quantified. And then we can specify an additional clause here that says how the ith element of the vector gets modified. It basically states that the new value of the whole vector is the list xs, where the ith element is replaced with a symbolic reference to gamma I, the name for the returned reference. Okay, I won't tell you much about how RefinedRust proves this specification here now, but let me just mention that it's not trivial, and that's precisely because we have to reason about how handing out a mutable reference to the element respects the representation invariant of the vector that we defined on the previous slide, and this interacts in a lot of ways. Okay, so far we've used RefinedRust to verify a variant of Rust's vector library with about 120 lines of code in total. Most of the functions are pretty small, but the whole thing expands to about 1,000 lines of code in our operational model, which is close to Rust's mere intermediate representation. But specification sizes for these functions are pretty small and manageable. And I think we can get a fairly good degree of automation for the most of the functions, but we tend to need help for pure Coq side conditions, for instance about lists, which is down to Coq automation for these things not being very good in general. I would also say that RefinedRust is still somewhat slow, especially compared to verification tools for safe Rust. And this is partly due to the increased complexity of working with unsafe code and also working foundationally in Coq. Okay. So far, we've only looked at this small case study. So in ongoing work over the past few months, we've been working on applying RefinedRust to more things and scaling it up to be more practical. In one project, we're working on adding support for interior mutability. And together with folks from IBM Research, we are working towards verifying the memory safety and security of a practical security monitor implementation in safe and unsafe Rust, which is developed at IBM Research. And in the course of that, we've also added a lot of support for some of the more advanced features of Rust, like closures, and making RefinedRust more practical to use. So this is work in progress. Okay. In the paper, you can find a lot more details on the things I presented, mainly on the type system and the model of the type system, including several technical contributions, such as place types to capture intermediate states of the Rust type system in RefinedRust, more in-depth explanations of the borrow variables you saw in the getMut example, and syntactic types to enable layout generic proofs. Since I have some more time, I'll just tell you a bit about place types and zoom in on a small example here that kind of motivates how this happens in the RefinedRust type system. You can see here a pretty simple example program. It creates a tuple of two integers, 1 and 2, and then creates a mutable reference xr to the first component, and it uses this mutable reference to write 42 to the first component. And in the end, we assert that the first component is 42 because we modified it through that mutable reference. So while the reference xr is alive, the first component is inaccessible, and if you use Rust and have used it before, this is something that Rust's so-called borrow checker will tell you. But how do we track that in RefinedRust's type system? Well, in a sense, the borrow of x.0 here changes what we can do with x.0, so its type assignment in our type system should change. But then we have to figure out what type we need to give it. And for that, our key idea is basically that there are more types than just the types you see at the surface level in Rust. These additional types we call so-called place types, and RefinedRust features place types to describe the intermediate states of the Rust type system. In this super simple example program, let's look at how this would be checked by RefinedRust by following the states of the type system. In the first step after the initialization of x, we would get a type assignment that states that x is a place in memory containing a tuple of integers. I'm omitting a bunch of things here, among them the refinements of the refinement types, but bear with me. In the first step then, after doing the mutable reference, then there was something interesting happening. First of all, we get a type assignment for the reference xr, of course, saying that it's a mutable reference. But more interestingly, the type assignment for x also changes by making the first component of the tuple blocked. And this is using one of our place types called blocked, which mentions here the lifetime a of the reference. And this means kind of that we can't access the first component of the tuple until the lifetime a ends. And then the rest is fairly uninteresting. We do the assignment, this doesn't change the types. And then a is implicitly ended by rust as x is accessed again. So RefinedRust makes x fully accessible again. Okay, and that's it for my talk. Thanks for listening, and I'm happy to take any questions and chat with you.
Yeah, questions in the front mic, please.
Have you explored verifying linked data types like linked lists or binary search trees? Because I think like one canonical example of something that's easiest to implement with unsafe code is like a double linked list.
Right.
Yeah.
We haven't explored that. We don't support recursive types well currently. That is something we are working on as part of the project of making it more real.
Okay. Thank you.
But it's definitely interesting.
Yeah. Yeah. Thank you.
Waiting for the next question, I have a question. Do you happen to support concurrency or plan to support concurrency?
So our operational model is kind of naturally, or our proofs are naturally concurrency aware. We haven't verified any programs that actually use concurrency, so that would be something interesting to do in future work.
Okay, let's thank the speaker.